In the previous section, we mostly talked about U substitution. In this section, we're going to be talking about integrals with exponential and logarithmic functions, but we're still going to be using U substitution to solve most of the problems. Let's take a look and get started now. Remember that these types of functions are often used to model things like population growth, cell growth, financial growth, radioactive decay, depreciation of loans, resource consumption, many, many different types of applications. So they're certainly a very important part of applied mathematics. What we want to do today is we want to learn about the formulas for the integrals involving exponential functions and the integrals involving natural log. Now, when we look at the integrals of exponential functions, remember that we're coming from, first off, the derivative, and we're reversing the process to get the antiderivative. So remember that the derivative with respect to x of e to the x is in fact e to the x. Remember that e is not a variable. We use a letter to represent it, but it is still a constant. So this is an exponential function, a constant raised to a variable expression. The second one, of course, is if the base is not the number e, which is the Euler's number, about 2.7182818284599, and it keeps going because it's irrational. When we're looking at this, remember that when we take the derivative of b to the x, we get b to the x multiplied by the natural log of the base. You may ask, no, why didn't we get that with the first one? Well, we do, but the natural log of e is 1. And so we just get e to the x. That's why it's our favorite. Now we want to undo this process. So we want to look at the integrals of exponential functions. So we have the integral of e to the x dx, which is going to be equal to e to the x plus a constant. So the integral of e to the x is e to the x, just as the derivative of e to the x is e to the x. Now, when we look at the integral of b to the x dx, we don't have this natural log of b that is present in the derivative. So we're going to have to compensate for that by dividing by it because it should have been there in the original, but it wasn't. So the integral of b to the x is also b to the x divided by the natural log of the base plus c. A common mistake when dealing with exponential functions is to want to treat them like polynomials, specifically like power functions, a variable raised to a constant power. This is not allowed. They are not polynomials, and they are certainly not power functions. We cannot apply the power rule when we have e to an expression involving the variable or some other constant raised to a variable power. It's simply not allowed. Now let's take a look at what is allowed. What we're going to do is we're going to evaluate this one right here, which is the integral of 2x cubed e to the x to the 4th power. Remember that we've done U substitution. So now what we want to do is we want to take a look at this expression. Let's evaluate. Remember that good places to find U would be in the powers of exponential functions. Bases of polynomial functions are power functions, but in the power for an exponential function. This is exponential because the base is a constant e. If we allow the power here to be our u, then we would have basically u equal to x to the 4th. Then remember that we have to find the derivative of u in order to substitute out the dx. We also have to find the derivative of the inside function. This is basic U substitution. So what we do is we take the derivative with respect to x of u, and we take the derivative of the other side as well. The derivative of u is just du dx. And then the derivative of the other side, here we can apply the power rule because we have a variable base to a constant power. This is when the power rule is applied. Variable base, constant power, not when you have an exponential function, constant base, variable in the exponent. Totally different, reverse situation. So we can apply the power rule here, which makes it 4x cubed. Then we abuse the notation, and this leads us to write that du is equal to 4x cubed dx. That happens by swinging the dx around to the other side as if it were a fraction and not, in fact, the derivative operation. It is the derivative operation, and we are abusing the notation. It shouldn't be allowed, except that it works, so we do it. So now we have du equals 4x cubed dx. What we want to do next is solve for dx, so we can substitute for dx in the expression of the integrand. So then we have dx is equal to du divided by 4x cubed. Now we substitute these into the integral. So we have 2x cubed, e to the x to the fourth becomes e to the u, and dx becomes du divided by 4x cubed. Now we've got a 4x cubed here in the denominator, and we've got a 2x cubed here in the numerator. The x cubed is going to cancel the x cubed, and the 2 over 4 will leave us with 1/2. So we end up with the integral of 1/2 e to the u du. The 1/2 is a constant, which comes out to the front, and we have the integral of e to the u du. Now we know from what we did a moment ago that the integral of e to the u du is in fact just e to the u. So this gives us 1/2 e to the u plus some unknown constant. And then the last thing we want to do is back substitute and go back to what the original expression was for u. U was up here in the beginning, x to the fourth. So we want to replace our u with the expression x to the fourth. So our final answer becomes 1/2 e to the x to the fourth power plus an unknown constant. That's the antiderivative function. Now let's take a look at example 2. Example 2 is different from example 1 in that example 1 was an indefinite integral. Remember, the indefinite integral gives you the antiderivative function up to a constant c. The definite integral, on the other hand, with limits of integration on the integral symbol, gives you the area under the curve between the curve and the x-axis from x equal a to x equal b. Let's take a look at solving this problem. The strategy is basically to start the same, but at the end we have to remember to plug in the limits of integration into our antiderivative function and subtract them to get the area between the curve and the x-axis. Now we're looking at the integral from 0 to 2 of e to the 2x. When we're looking at this, this is again an exponential function, constant base, variable in the power. In order to do this, we look to the power to represent u. So in this particular problem, we want u to be equal to 2x. Then we take the derivative of both sides with respect to x, the original differential that you see in the integral, and the derivative of u will just become the derivative of u with respect to x. The derivative of 2x, on the other hand, becomes the constant 2. Then we abuse the notation by swinging the denominator dx around to the other side so that we have du is equal to 2 dx. Then we solve for dx by dividing both sides by 2 to get dx is equal to du over 2. Now, because this is a definite integral and because the original limits of integration are x values, when we're switching to u, we need to change the limits of integration. This is generally a faster and more efficient way to solve the problem, even though most students have a tendency to want to keep the x limits of integration and back substitute. That does work as well, but it's actually a little bit more work. We're going to instead find the new values for u. When x is equal to 0, remember that our definition for u is up here. U is equal to 2x. When x is 0, u is equal to 2 times 0, which is 0 as well. When x is the upper limit of integration 2, then u is equal to 2 times 2, which gives us a new upper limit of integration of 4. Now we're going to substitute these into the original integral, substituting each piece using the parts that we found. So now I have a new integral with u limits of integration from 0 to 4 of e to the u, and then dx is equal to du divided by 2. That makes the divided by 2 a constant, which can be pulled to the front. This gives me 1/2 the integral of e to the u du from 0 to 4, which of course is just 1/2 e to the u evaluated between 0 and 4. Now we can leave the 1/2 on the outside, and we can then plug in the limits of integration. We have e to the 4th minus e to the 0. Remember that e to the 0 is a constant, it is 1. This gives us 1/2 of e to the 4th minus 1, which is equal to 1/2 e to the 4th minus 1/2. This is the area between the curve and the x-axis from x equals 0 to x equal 2. The link that you see here is a Desmos link that will take you to that graph. Let's take a look at it right now. When we look at the original graph, we can see the exponential in its typical shape, which goes like this, and it goes up forever. We're looking at the area between the curve from x equals 0 up to x equal 2, where those two vertical lines are. The exponential is always above the axis unless it has been translated down. That makes all the areas strictly positive and above the x-axis, and it's shaded blue in this particular region here. If you want to know how much that area is, you need to return to our paper and compute what 1/2 of e to the 4th minus 1/2 is. Take a moment and let's do that now. 0.5 times e to the 4th minus 0.5. That gives me about 26.8 square units of area. If we look back at the picture, we can see that that does make sense. It is about 26.8 or about 27 squares that we see under the curve that are shaded blue. Let's now move on to the next example, example 3. In example 3, we're again doing a definite integral, noted because of the limits of integration. Again, we see that we have an exponential function, e to the 4x to the negative 2. We also have another function present, a rational function, 1 over x cubed. So now we need to decide what is going to be u. Our choices are 1 over x cubed by itself, or the power on the exponential. Generally speaking, the power on the exponential should be your first choice. So when I look at that, I'm going to take u to be equal to 4x to the negative 2. When I do that, I need to remember to take the derivative with respect to x of both sides of the equation. This is then going to give me du dx on the left, and then I'm going to apply the power rule on the right. Power rule because the base is the variable x and the power is a constant negative 2. The 4 is a constant coefficient, which just sort of tags along. I bring the negative 2 to the front to multiply by the 4, so I get negative 8x to the negative 3. Remember that negative exponents can be written in such a way that they are in the denominator with a positive exponent. So negative 8x to the negative 3 becomes negative 8 over x cubed. Now look back at your original integrand. What was behind the integral symbol before the differential? I've got a 1 over x cubed, and I can see that in my derivative of u with respect to x, I also have an x cubed. I've got a constant negative 8, but constants are easy to manipulate. So now what we're going to do is we're going to abuse the notation, swing the dx to the other side, and then solve for the dx. So I get du is equal to negative 8 over x cubed times dx. The next thing that I want to do is I want to solve for dx by multiplying both sides by the reciprocal of the fraction. So this gives me dx equal to x cubed over -8 times du. The next thing I want to do is substitute each piece into the original integrand. However, because it's a definite integral, I need to change the limits of integration. Remember, you can keep them as x variables or x constants, but then you have to write x equals. Let's go ahead and change the limits of integration so that we don't have to back substitute to x, we can stay with u. When x is equal to 1, my u expression is 4x to the -2. So this leads to 4 times 1 to the -2 power, which is 4 over 1 squared, which is still 4. When I have x equal to 2, I have u is equal to 4 times 2 being raised to the -2 power, which is 4 over 2 squared, which is 4 over 4, which is equal to 1. Now that I have new limits of integration, make sure that you put them in the correct locations. We're replacing the lower limit of integration 1 with 4 and the upper limit of integration 2 with 1. Yes, it's backwards, but that's the correct substitution. Now we're going to go ahead and make the substitutions here. This leads to the integral from u equal 4 to u equal 1. And our 1 over x cubed will stay. And then our e to the negative, or to the 4x to the -2 becomes e to the u. And then we need to replace the differential dx that we see here with what dx is equal to, which is down here. So the differential dx gets replaced by this x cubed over -8 du. Now notice that the x cubed and the x cubed in the denominator are going to cancel. The -8 in the denominator is a constant which can be pulled out of the integral, and that will leave me with e to the u du. Let's write that down. We have 1 over -8, the integral from 4 to 1 of e to the u du. The integral of e to the u, the antiderivative, is e to the u. So this gives us the 1 over -8 e to the u to be evaluated between 4 and 1. Now remember that special rule for integrals that says if you have a negative constant, you can switch the limits of integration, which will eliminate the negative. This would make it easier since that way we don't have to track the negative. So this makes it a positive 1 over 8 e to the u, and we switch the limits of integration to go from 1 to 4 to compensate for having removed the negative. That's one of the rules for integration. Now we can leave the 1/8 outside and substitute the limits of integration in. And so we end up with 1/8 times e to the 4th minus e to the 1st. And that's a decent way to leave the expression. Now, if you want, you can click on this link right here, and this should take you over to a Desmos graph, which shows you the graph between the original values x equal 1 and x equal 2. And you can see this expression right here. Notice that the graph of 1 over x cubed e to the 4x to the -2 has two pieces, one below the axis and to the left of the origin, one to the right of the axis and above. When we're integrating from 1 to 2, we want this expression here. Notice that's very narrow and goes up very, very high. So this area underneath the curve is what we're looking for. Now let's take a look at example number 4. On example number 4, we have the integral of 3 to the -x. Now this one is a little bit different because the base is not e. What that does is it's going to introduce a constant, which is the natural log of the base. So we're going to have a natural log of 3 in the denominator, since the base is not e. Now we're going to do u substitution again. It is exponential because the base is a constant and the variable is in the exponent. And again, the natural place to look for u is in the power. So again, we have u substitution with u being the power on the variable. We take the derivative with respect to x of both sides. And that gives us du dx equal to -1. Abuse the notation and swing the dx around to the right side to get du is equal to negative dx. That means that dx is equal to negative du. We'll use that to substitute for the differential in the original integral. Now we need to take a look and see if it was a definite integral or an indefinite, so we know whether or not we need to substitute out the limits of integration. This one was an indefinite integral, noted because there are no limits of integration. So the integral of 3 to the negative x power dx will give us a antiderivative function up to a constant c. So now we want to substitute the pieces that we have. So we have the integral of 3 to the u, and we replace dx with negative du. The negative becomes a constant, which can be pulled to the front as a -1. This becomes basically -1 times the integral of 3 to the u du. Now the integral of 3 to the u, as we saw at the very beginning, is going to be 3 to the u divided by the natural log of the base. The base is not e, and the natural log of e is 1, so it remains natural log of 3. Now this is an antiderivative function, so we have this only up to a constant plus c. Now the next thing we want to do is we want to replace the u with what it originally was to go back to x. Since the original integral was in terms of x, the antiderivative function needs to be in terms of x. So that gives us, as a final answer, -3 to the negative x divided by the natural log of 3 plus a constant. This is the antiderivative function of the original integrand function 3 to the negative x power. Now let's take a look at some natural logs. Now we want to take a look at some integrals involving logarithmic functions. To remind us how we get these, remember that the derivative with respect to x of the natural log of x is equal to 1 over x times the derivative of the argument itself. This is the u form. The derivative of the natural log of u is 1 over u times the derivative of u with respect to x. Now the derivative of x with respect to x is just 1, so we end up with 1 over x. That means that when we want to undo the process and do the antiderivative of this, we'll be starting with 1 over x, or x to the -1 power. When you have x to the -1 power, then you can go backwards. So what we're looking at then are the integration formulas that you see here. When we're looking at these, we have the integral of x to the -1 dx, which is equal to the integral of 1 over x dx. When we undo the derivative, we get the natural log function. But because natural log will only accept strictly positive arguments, we're required to put absolute values around the argument x. And this is the antiderivative function up to the constant plus c. Please note that these absolute values are absolutely required. Don't forget them. Natural log will not accept anything but a strictly positive argument. Now, the next two are things that you're actually going to prove in Calculus 2. We state them here for completeness, but I'm not going to expect anyone to memorize these formulas because we'll learn a better way called integration by parts of finding these in Calculus 2. This is the integral of the natural log of x dx. And its formula becomes x times the natural log of x minus x plus the constant of integration. That is x natural log of x minus x plus the constant of integration. And again, we'll prove this in calculus 2. What if you have the integral of a log where the base is not e? Well, it's basically the same expression as above with natural log, but you have the natural log of the base divided. In other words, you have a constant introduced. It becomes x natural log of x divided by the natural log of a minus x divided by the natural log of a plus the constant of integration. Or you can factor the x and the natural log of a out and have x divided by the natural log of a times the natural log of x minus 1 plus the constant of integration. Let's take a look at a couple of examples that involve natural log. In example 5, you can see that we have the integral of natural log of x divided by x dx. When we're looking at this one, again, what comes to mind is u substitution. It's not one of the formulas that we can directly find the antiderivative function for. We can't use the power rule, and it's not one of the trig functions where we know what the antiderivative is. When we look at this, we have two choices for u, or maybe three, depending on how you divide it up. Natural log of x is one choice for you. X by itself is a choice for you, and 1 divided by x is a choice for you. In this case, I think it's helpful to actually rewrite this one as the natural log of x times 1 over x dx. This is helpful because the derivative of natural log of x is in fact 1 over x, which means that I can make natural log of x be u, and the derivative is also a part of the integrand. So I choose for this one to let u be natural log of x. So u is equal to natural log of x, and then I take the derivative with respect to x of both sides. When I take the derivative with respect to x of the left, I get the typical du dx. On the right side, I get 1 over u times the derivative of u with respect to x. But u is just x, and the derivative of x with respect to itself is 1. So this gives me 1 over x. Then we abuse the notation by pushing the dx over to the right side to get du is equal to 1 over x dx. Then we can solve this for dx by swinging the x to the other side, and that gives us dx is equal to x du. Now we can make a substitution into the original integral that you see up here. This is going to be the integral of u divided by x times x du. Again, I substituted natural log of x became u. The 1 over x stayed 1 over x, and dx got replaced by x du. Now the x's cancel, and I get the integral of u du. When I look at the integral of u du, now I have u to the first power. If I have u to the first power, where the variable is now in the base, and I know it's the variable because I have the differential du, that's what tells me u is the variable, then I can apply the power rule. So I apply the power rule, which means I add 1 to the power and I divide by the new power. And then because it is an indefinite integral, I get it up to a constant of integration, a family of functions. This is the antiderivative function in terms of u. But I want the antiderivative function in terms of the original variable x. So I back substitute what u is. U, of course, was the natural log of x, and it's being raised to the second power. So I can then write the answer as 1/2 the natural log of x quantity squared plus c. Now, in some textbooks, you will see the 2 written between the natural log and the x, much like we do with trig functions. I prefer not to do that because I think it's clearer when you write it in parentheses that the natural log, the entire function itself, is being squared. We have natural log of x times natural log of x. Now let's take a look at example 6. In example 6, we have 1 divided by the quantity x times the quantity natural log of x being squared. So again, we see that this isn't one where we can directly apply the power rule. It's not a trig one. So again, we're probably going to do u substitution. What is a good choice for u? Denominators are good places to find u, and so is the base of an expression raised to a constant power. So that makes natural log of x a really good choice for u. Plus, I can see that I have 1 over x, which is the derivative of natural log of x. Let's write this in a more expanded form so you can see the pieces. This becomes 1 over the natural log of x squared times 1 over x times dx. Then I could actually think of the natural log of x as u, and I could actually, if I wanted to, write this in the numerator by changing the sign of the exponent from 2 to -2. This would make it the integral of 1 over x times the quantity natural log of x to the -2 dx. Now it seems more clear that I should choose natural log of x for u because I can see the derivative of it already in the integrand. So I choose u to be natural log of x, and we've done this several times already. So we know that du dx is going to be the derivative of both sides, derivative of natural log of x, and the derivative of natural log of x becomes 1 over x. Then we abuse the notation by pushing the dx to the other side. This is the genius of Leibniz's notation. And we get 1 over x dx. Then we solve for dx by pushing the x to the left side by multiplying by it. And we get dx is equal to x du. Now we're going to substitute each piece into the original integrand. We're going to substitute u for natural log of x, and we're going to substitute x du in place of the dx. Let's go ahead and substitute now. This becomes the integral of 1 over x times u squared times x du. The x in the numerator and the x in the denominator cancel, and I get the integral of du over u squared. Now I can push this to the numerator as I did up here when I was thinking of it as natural log, and that will make it the integral of u to the -2 du. Now, because the differential is du, I know that the variable is u, and that means I can apply the power rule to u to the -2. So I add 1 to the power, so it becomes -2 plus 1, and divide by the new power -1, and add on my constant of integration because it is an indefinite integral. Don't forget the constant of integration. It's a very important part of the antiderivative function. This then becomes negative u to the -1 plus c. I can also write this as -1 divided by u plus c. Now I need to back substitute because the original integral, what we can see up here, had the variable x, noted because the differential is dx. I need to return the antiderivative function in terms of x. My u was natural log of x, as you can see right here. So I'm going to back substitute natural log of x in place of u. Coming down here, this gives me -1 over the natural log of x plus a constant. This is the antiderivative function of the original integral. In our next video, we'll take a look at finding the antiderivatives of inverse trig functions, which is always quite a challenge and actually involves a lot of pattern matching.